Hi folks, and welcome back to Math with Captain Rod. I'm making this video here again to provide an example of how to set up an integral for a surface area, specifically a surface area generated by taking a curve and revolving it about a specific axis. So what we're going to do is we're going to look at the curve generated by x times y equals 1. I've drawn it, I've already sketched it here in the first quadrant. This thing has a vertical asymptote at x equals 0, and it's got a horizontal asymptote because the limit of this function here as x goes to infinity is 0. We're going to look at it in the region where y equals 6 to 8, and we're going to look at the curve revolved about, we're going to look at the surface you get by taking this portion and revolving about the y-axis. Alright, so let's say that here's the 8, and I'm going to not do this to scale, and here's the 6. It's not important that this is not to scale here. And you start all of these by drawing your differential element, ds. Now, in this example, we're going to be revolving this curve about the y-axis. So if we do that, the ds here is going to create a ring. It's going to look like this. I'll go ahead and draw this kind of off to the side here. There's my ring here. The radius of that ring is this distance, which, if you look at the picture, that's equal to x. This dimension is the ds, which is equal to square root of 1 plus dy dx squared times dx, or we could also write it square root of 1 plus dx dy squared dy. That was a dx. Depends on which one you try to set the integral up with respect to. It doesn't really typically matter. Alright, so the surface area of this ring is going to be a differential surface area, and it's going to equal 2 pi r, right, that's the circumference, times the ds. Now, I'll just start putting values in here. For now, the 2 pi r, the radius of this ring is equal to x. Let's write this 2 pi x times ds. The ds, we can write square root of. Now, at this point, we've got to make a choice on whether or not we want to write this integral with respect to x or y. Because I've got an x here, I guess I'll go ahead and set it up with respect to x. So this is going to be 1 plus, this term will be dy dx squared. Now, last time I did this, I goofed this up, so I'm going to be kind of cautious here. Here's my y, so dy dx is going to be minus 1 over x squared, because this is x to the minus 1. So this term, by the time we square it, is going to be 1 over x to the 4th dx. Alright, so here's our expression for dA. Our total area then is going to be the integral 2 pi x times square root of 1 plus 1 over x to the 4th dx. Now limits, be kind of careful here. The limits are not from 6 to 8. These were y values here. So, and you always want to integrate kind of in a forward sense here. So if we change this to limits over x, we're going to be integrating along this curve, then the first value we'll get from here. So where you get your limits is, you put 8 in for y, solve for x. It's pretty easy. I get 1/8. And then we integrate along this curve. I'll go ahead and put 6 in for y, and solve for x. You get 1/6. So there is the setup for the surface area of the geometry you get when you take this curve. I'll draw the curve in red, and revolve it about the y-axis. That's actually going to give you this ring here that's going to look something like, not really a ring, it's going to give you this kind of bottle top looking geometry. Oops. Good enough. Right, and here's the integral that will calculate the surface area of it for you. I hope that this video helps. Have a great day.